Hello and welcome. Today we are going to be talking about distributions and z-scores. So, when examining data using histograms, we like to describe the shape of the overall pattern and what we see. Now, what we see here first is called a rectangular distribution. This happens when all the values have the same frequency. If you were to roll a die many times, then the numbers 1 through 6 would happen about the same number of times. For example, if you were to roll a die, say 600 times, then you would probably expect to see a 1, a 2, a 3, a 4, a 5, or a 6. And then this other one, well, we'll just like pretend like it doesn't exist. But you would expect to see all of those others happen about 100 times each. Now, it might not be exactly 100. Maybe one would happen a little bit more and one would happen a little bit less. But in general, if you were to roll a die 600 times, you would get a distribution that looked about like this, where you would get 100 of each of those outputs. So when you have the same probability of each event happening, looks something like that. This next one is called a bimodal distribution, and it happens when you have two values that occur more often than others. It's bimodal, bi meaning two, and then mode meaning the most. You can see right here is one of the modes, and here is another maybe local mode, so to speak. It's like a local maximum. So even if those aren't both equal, we can still have a bimodal distribution. And one of the examples that I like to see, I know I have an example written here, but also if I were to look at the heights of all the people in a kindergarten classroom, I know that might be very specific, but the heights of everyone in a kindergarten classroom would probably look something like this. Now, you might say that's kind of weird. Why? Well, in kindergarten, you have a lot of kids. And most of those kids that are in that kindergarten range are somewhere between about 3 and 4 feet tall. I might even be a little bit on the high side here. But a lot of those kindergartners are around 3 feet tall, maybe 3.5 feet tall. And then you can see there's this little dip right here where it comes down to almost nothing. And then we have another little bump. It's not near as high as the others, and hopefully you have this figured out. There's other people in a kindergarten classroom besides those adorable little 5-year-old children. So we also have teachers, right? We have the teachers, we have the aides, we have the principals, we have other people coming in, and they are typically taller than 3 or 4 feet. My wife is a kindergarten teacher, and she is taller than most of the kids, right? And so you have this big distribution, or you have a lot here between 3 and 4 feet tall, and it comes down to almost nothing, and then you have a lot between about maybe 5 and 6 feet tall. So this is an example of another bimodal distribution. Um, this next one then is a distribution that is skewed right. And what happens with this is it tapers off to the right. I remember these are skewed right by making them into a little mountain, and I think about which way I would go snow skiing down it, or which way you would go snow skewing. And so you would not want to go off to the left of this. That would be a hard fall. Yikes, I don't want to do that. But this has a tail that kind of goes off to the right. And so if you were going to go skiing down this mountain, you would go skiing to the right. This one is skewed right. So you can go snow skewing down the right side of this. Most distributions involving household income are going to be right skewed. And in the United States, most households are between 30,000 and 120,000. And so that's a big chunk of the the distribution of people and the money that they make. But then as you continue to go up, to 300,000, to 500,000, to a million, to 5 million, whatever it is, you can see you get fewer and fewer and fewer people making those amounts, but it does tail off to the right. Like there's still some people that make $10 million a year, right? But we can only make so little. You can only make as little as zero. So when you have a distribution that maybe has an unlimited high amount, and a lot of them are focused down on the lower amount, then this is a skewed right distribution. Also, we also have a skewed left distribution, and it's the same idea, maybe where you have kind of a tail off to the left-hand side, that would be skewed left. Okay, there are other distributions as well. These are just some of the main ones. Another somewhat famous one is a J-shaped distribution. It might look kind of like that, or an exponential. Those are also considered J-shaped. And these actually happen pretty frequently. If you were to go and look at Amazon reviews, what you find that people do something like this when they give their star ratings, 1, 2, 3, 4, and 5. Most things that when you look at, they have a lot of 5-star ratings and then some 4 stars, very little 3 stars, almost no 2 stars, and then back up a little blip for this 1 star. And this just happens a lot, right? And that's where you kind of get this J-shaped distribution. So that's one area where you kind of do that, and it can go either way. Um, Now, those are all nice distributions and all, but one of the more common ones, and the one that we're going to be spending a big chunk of time on, is called a normal distribution. You can see that with a capital N, normal. That's actually its name. And some of the properties of a normal distribution, well, you might see it down at the bottom of the page already, but a normal distribution you've probably seen before. It's just this bell curve, right? So it's called a normal curve. The normal curve is bell-shaped and it's symmetric about the mean. The mean, median, and mode all have the same value and it's right at the exact center of the distribution. 50% of the data is lower than the mean and 50% is greater than the mean. Now, normally in all these other distributions, we could say that 50% of the data is lower than the median because the median is like that value right in the middle. So 50% is below the median, 50% is above the median. But it just so happens that in a normal distribution, this peak right here is the mode. It's also the 50% mark, which would be the median, and it's the balancing point. If I were to take a small little fulcrum and like a little teeter-totter, and if I were to uh, try to move that around, maybe. There we go. Okay. If I were to say, like, where does this balance? Well, it balances right in the middle. And where it balances is the mean. So it just so happens the mean, median, and mode are all in the same place. If I go back up here and look at one of these other distributions, the median is the 50% mark, right? Where 50% of the area is to the left and 50% is to the right. If I was to, just ballpark it, if I was just approximating it here with this one, I would say the median is probably somewhere about in here. Okay, and if you go through and you add up the area to the right and you add up the area to the left, that would be about the same. And so that might be the median or the equal areas point. And the mean of this, because it's skewed to the left, the balancing point is actually going to be pulled just a little bit to the left of the median. The mean is pulled slightly in the direction of the tails or the skewedness. If you were to set this on a teeter-totter, the mean would be just a little bit more to the left than the median. Okay. All right, and then also on this one, then this would be the mode. So you can see the mean, median, and mode are oftentimes very different numbers. But in a normal distribution, it just so happens they're all right in the middle. Now, when data is normally distributed, what we would say is that about 68% of all the data lies within one standard deviation of the mean. Remember, standard deviation is talking about how far on average the points are away from the mean. Okay, so if we go out to the right one of those, one standard deviation, and to the left one standard deviation, then about 68% of data will be in there. And about 95% of the data is within two standard deviations, and 99.7% of data is within three standard deviations when you have normally distributed data. Now, this rule, or this empirical rule, as it's called, also has another name. So it is called the empirical rule. It's also called the 68, 95, 99.7 rule. And I know that might seem kind of weird, but I'm telling you, you can definitely Google search that, and you'll find all the same information as if you find the empirical rule. So just a lot of people tend to call it the 68, 95, 99, 7 rule. When you look down here, you can see a normal distribution that has been split up, and you can see a whole bunch of different percentages. The first percentage that I want you to kind of make note of or observe is that right here is 68% of the data. Okay, if we start in the middle and we go to the left one standard deviation and to the right one standard deviation, then about 68% of that data is going to be within one standard deviation. And of course, if that's 68%, you can cut it in half, and that's where we get 34% is in each one of those little sections. And then if you were to go out one more standard deviation, if you were to go 2 standard deviations to the right and 2 standard deviations to the left, you can see that's actually 95% of the data. And so if 95% of the data is there and 68% of the data is in here, then we can find that leftover amount as well. So if we take 95 minus 68, I get 27. That means 27% is going to be shared between these two amounts, right? So if 95 is this much and 68 is this much, when we subtract those two, then that gets us 27%. We split that between you can split that in half, and that's where we get our 13.5 for each one of those sections. Now we do the same thing when we find the last one, right? What we'll do is if we go out 3 standard deviations, we go 1, 2, 3 to the right and 1, 2, 3 to the left. Well, we already know that 95% of the data is here, and we know that 99.7% of the data is there. And so if we once again subtract those, we can take our 99.7 minus 95, leaves us with 4.7% that's going to be shared between these two little sections, this section on the left and this section on the right. 4.7% of the data is split between those two, and so you cut 4.7 in half, and that's where you get 2.35%. Now these are approximations, but they're reasonably accurate. And then what we have left then is you can see 99.7% of the data is within 3 standard deviations. So that means that 0.3% is outside of that. 0.3% is to the left of there and to the right of 3 standard deviations. So once again, if you take that 0.3% and split it in half, that's where we get 0.15%, and that's how we get this, these little bits on the end. Now again, these are approximations using this lovely 68, 95, 99, 7 rule. We actually have some computers and calculators and z-tables that help us to get even more accurate than this, but these are nice ballpark numbers. Before we go on, I do want to take just a minute and maybe give you an example of where you might see a normal distribution and put a little bit of context to this. So in the United States, the heights of adult males in the US average around 5 feet 9 inches. So we use this funny looking U. It's actually the Greek letter mu, and it's just like a cursive U, but it just means mean. So that the mean is 5 feet 9 inches. And then we also have the standard deviation of 3 inches. So that means that on average, adult males in the US, they vary from the average by about 3 inches. So if you think about that, and if we go up 3 inches, that would take us to 6 feet. And if we go down 3 inches, and you start considering all of the adult males that you know, about 68% of them are going to be between 5'6" and 6 feet. And so a big chunk of the adult males that you know are between those two values. Then when you start going out a little bit more, if we go up another 3 inches, that takes us to 6'3" and down to 5'3". And this is approximate. It's not exactly a standard deviation of 3. I just wanted to use some nice numbers. But if we go up 3 more inches and down 3 more inches, so now we have a range of 5'3" up to 6'3". And when you consider all of the adult males that you know, well, that's going to be about 95% of all adult males are in this range. So I look at my life and I think about all the adult males that I know. Yeah, a big chunk of them are between 5'3" and 6'3". I know a couple people that are taller, and it does depend on the circles that you run in. For example, I played basketball growing up, and I have a lot of friends that play basketball. So in general, I have a lot of friends that are a little bit taller than average because that's the circles I run in. So like actually do know quite a few, well, probably more than average people that are taller than 6'3". I'm 6'3", right around there. Now, if you go up another 3 inches and we go up to 6'6" and down to 5'0", 99.7% of all adult males in the United States are in this range. So down to 5 feet and up to 6'6". So really kind of think about this for a minute. All the adult males that you know in your life are probably between these two numbers. Now that you know personally, I know we can all name people that are taller than 6'6" or shorter than 5 feet nothing, right? We can name some. There's some very famous ones. Like I said, basically every player in the NBA is pretty much taller than 6'6". But as far as people that you know personally, you know what? I probably only know one or two people that are actually taller than 6'6". Right, and I don't know. Maybe I know adult males that are shorter than 5'0", but it just shows you that the vast majority that you know are going to be within one standard deviation, and then you get fewer and fewer and fewer the further out you go. Okay, that's all. That's all a normal distribution tells you. As you move up standard deviations and down standard deviations, you get fewer and fewer and fewer people that you know of that height. All right, so let's get back to this then. And suppose the daily number of steps taken by users of some particular fitness app is normally distributed or approximately normally distributed. If 2,400 users are active on the app each day, how many users are expected to take within one standard deviation of the mean? Now, here's the great part about this is we don't even have to know the mean. We don't have to know the mean. We don't have to know the standard deviation. We just know that, you know what? About 68% of all the users are going to be between or is going to be within one standard deviation of the mean. And it tells us there's 2,400 users. So 68% of 2,400. That's about how many people or how many users are going to be within one standard deviation. So we'll take 0.68 of means multiply and then 2,400. That's 1632. So 1,632 users are within one standard deviation. And when it says within two, well, remember, we know that it's the 68, 95, 99.7 rule, right? So within two standard deviations will be 95% of 2,400 users, or 0.95 times 2,400. 2280. Let's go ahead and look at some more normal distribution graphs. Suppose that the mean number of hours of people that sleep per night is 7 hours with a standard deviation of 1 hour. These problems are just made up, so I don't know that that's necessarily true. Don't take this for a scientific study. This is just to kind of make some nice numbers here. What percent of people sleep at least 7 hours? Now, you have a nice normal distribution here. I do want to take just a minute and show you how you can make a nice normal distribution if you're not given one. So whenever you're doing your homework on regular paper and you're not given a normal distribution, one thing you can do is you start out just by making You're just going to make a straight line however much room you have. It doesn't really matter. There you go. And we're going to go right to the middle of that line, and our mean goes there. They tell us the mean number of hours is 7, so I'll put 7 right there. And then what I'm going to do is go 3 lines up. 1, 2, 3. Those are 3 standard deviations, and we'll go down 1, 2, 3. Try to keep them as equally spaced as you can. That last one wasn't very good. So try to keep them equally spaced. And then what we're going to do is from 7, we're just going to add 1 standard deviation and keep going all the way up. So each standard deviation is 1, so we just go up by 1 each time we go to the right. So this would be 8, 9, 10. And when we go to the left, we're going to subtract 1 standard deviation. So that's 6, 5, 4. After that, we're going to draw a vertical line, however tall that you want your graph to be. That's going to be the highest point. From there, for 6 and 8, or whenever we go out 1 standard deviation, you're going to draw another line that's about 60% as tall as what you did. So just a little over half. That's all. So we go up a little over half, and then we're going to go up about a quarter. And then for these last 2, I'm actually not even going to go up at all. I'm just going to use the length of the line that I have there from that initial little hash mark. What this does is it divides us up and it gives us some regions that are nice. And then we're going to essentially connect the tops of all of these with a smooth flowing curve. One other thing that's kind of interesting about a normal distribution is this is actually concave down here like that. And right there at that spot, the concavity changes. It kind of does one of these. Now I did it way extreme so you could see, but it kind of comes down and changes concavity, and we'll continue out that way. It doesn't ever touch the x-axis. Same thing over here on the right. This is concave down until it gets to there, and now it changes. That's called an inflection point. And when you get into some higher level math like calculus, that's really important. It's not as important here, but it will continue on that way. Now you have a reasonable looking normal distribution. From there, you could then put in the numbers that we learned. Remember, we have within 1 standard deviation is 68%, so we cut that in half. And this is 34% in each one of these. Then remember, we have 95%. So if you forget how much goes in each one of these little sections, you can do 95 minus 68, get 27. And then you take 27 cut in half to be 13.5%. That's where we get the numbers that go in here and in this standard deviation. Then once again, we have 99.7% for the next one. So we would do 95, or 99.7 minus 95 is 4.7% to split between the two of them. And that's where we get our 2.35% on the left and the same on the right. Lastly, if 99.7% is all taken care of, that only leaves 0.3% to be split up into these last little bit of tails. So that's 0.15. You can absolutely memorize it. You can put it on a note card, whatever you need to do, but it's also not that hard to just kind of create it once you do it a couple times. Now we can say we're ready to answer these questions. How many sleep at least 7 hours? Or sorry, what percent of people sleep at least 7 hours? Well, here's 7. What we could do is we could add up all of these numbers because it says at least 7, and at least means greater than 7. 7 or greater. But man, that seems like a lot of work. Because remember, right there in the middle is the mean, median, and mode. That's just 50%. That's the equal areas point. So what percent sleep at least 7 hours? 50%, right? If you were to add up the 34, 13.5, 2.35, and 0.15, those will all add up to 50%. I'm just not going to take the time to do it because I know it's right in the middle. Next one says, what about sleeps between 7 and 8? Well, I took a minute and I actually made a nice graph and I labeled everything, so there's really not any work to do. It's just 34%. That's all. less than 9 hours. So now what we want is, here's 9, and we want all this amount over here. So we could take a minute and we could add all these up. That would be just fine. The other thing that you could do is, we know that all the way up to 7 is 50%, and so then you really only need to add 50% plus 34 plus 13.5. That will work, but there's an easier way still. Do you see how we have everything colored in blue except for this over here? Like, what if we just added those two together and said that's what we don't want? Well, that's exactly what we're going to do. If you add 2.35, so 2.35% plus 0.15% is going to get us 2.5%. So from here over is 2.5%. And so if we want everything else that's to the left of that, that's going to be 100% minus 2.5%, 97.5%. Once again, you can absolutely get that by adding together all of these other values. It's just so much more work to do that. If you take a minute, you can check it. 0.15 plus 2.35 plus 13.5 plus 34 plus 34 plus 13.5. Those should add up to be about 97.5%. Now, sleep more than 8 hours. This one's probably just as easy to add up these last three if you want. So we can add those three together, and if you add the 13.5% plus the 2.35 plus the 0.15, those will add up to be about 16%. Now, between you and me, it's not actually how I do it. What I would do is, I know that the middle is 50%. I can add together, I can add 50 and 34 to get 84%. And so now I know that all this is 84%. So 100% minus 84% gets me the rest of this, which is just 16%. So that's how I would do that problem, but you can absolutely do it any way you want. Lastly, between 6 and 7 hours, this is another nice easy one because of our graph. Here's 6 and there's 7, 6, 7, 34%. All right. Next, I would encourage you now to go ahead and try to get this normal distribution completed instead of just watching me do it. Don't just write it down, but actually try to do it on your own. We know that it has a mean of 72 and a standard deviation of 8. Remember, we'll typically write that as a mu of 72 and a standard deviation of 8. So the 72 goes in the middle, and then see if you can get everything else situated. All right, let's go ahead and do this. All I'm going to do is add 8 to 72 to get to the next one. That's 80. Add an 8. That's 88. Add an 8. That's 96. Then what we'll do is we'll start subtracting 8 as we go to the left. So minus another 8 and minus another 8. Hopefully those are all right. If not, I'm sorry. I think you understand the point though. There we go. Next, we'll go through and put in our values for the percentages. I like to do the middle one first. So remember, these are going to be 34% each. Then we go down here. This is 13.5% in each one of these. Do you need to do every one of these? No. We could absolutely do it without that. But here at the beginning, we're practicing and we're doing repetition. We're writing these numbers over and over again, and that will help us to learn and remember. There we go. Now it says, draw a bell curve and determine the percentage of students who score at least an 88. I'm going to come over here at 88 and I'll draw, that's my cutoff right there. And when it says at least an 88, that means I want 88 or more. Like if you scored at least an 88 on a test, that means you might have scored higher than an 88. Some people get really confused with this. They see the word least and they think that's lower, right? No, this is saying 88 is the smallest. So if 88 is the smallest, we only want 88 and bigger. So that would be this way to the right. So we're going to add up this 2.35% plus the 0.15%, and that gets us 2.5% scored an 88 or higher. They scored at least an 88. Now, z-scores. Z-scores show in terms of the standard deviations how far a given score is from the mean. So for example, a z equals 1 means that the value is 1 standard deviation above the mean. Therefore, we would say 84% of the data is below the mean and 16% of the data is above the mean or to the right. Let's go back up to the one we did just a minute ago. We said that students scored an average of a 72 on this exam. And if we look at our standard deviations and we go 1 standard deviation above the mean, well, 1 standard deviation is right here. Right? There's 1 standard deviation. So 16% of the data is above that 1 standard deviation, and the rest, or 84% of the data, is below that 1 standard deviation, right? We go up 1 standard deviation. This z-score would be a z-score of 1 because that's 1 standard deviation. An 88, for example, would be a z-score of 2. A 96 would be a z-score of 3. If we go down, 64 would be a z-score of -1 because it's to the left. 56 would be a z-score of -2, and this would be a z-score of -3. You can see it is very, very rare for anyone to ever be lower than a z-score of -3. So, in fact, there's a lot of different ways that we can talk about outliers. I know we've talked about them in the past, but some people will just define outliers as any point that's less than z equals about 2.7. So if your z-score is smaller than 2.7, sorry, -2.7, or higher than +2.7, some people call that an outlier. Right? There's also the IQR rule. There's other ways of talking about outliers. There's not just one way. But you can see there's very few data points that are that far, that low, or that high. Okay. Now, a z-score of -2 is a value, let's see, z-score of -2 is a value that is 2 standard deviations below the mean. And when we go back up to here, right, here's a z-score of -2, and you can see that only 2.5% of the data is down this low, right? 2.5% is to the left, and that means that the rest of the data, or 97.5% of the data, is above that value. Now, z is the primary unit of measure that we use in statistics, and we use this when we're talking about a normal distribution. We talk about the number of standard deviations. Okay, so let's go ahead and we're going to start using this z-score a little bit. A z-score is calculated by taking our data entry minus the mean divided by the standard deviation. I know that formula may seem a little bit strange. A lot of times we shorten it down and we just write it like this: z equals x minus mu over sigma. Not everybody's into using all these Greek letters. You know, you're going to sound smart whenever you're talking to your friends and neighbors when you're talking about sigma and mu and all these other things. But let's make sure you do actually understand it. The data entry or the data point that you're using, I'll just call that x. The mean, right, that's the average, and that's usually given to you, but that's our mu. And then our standard deviation is our sigma. And of course, z is the number of standard deviations. Okay. I just like this other formula here on the right because there's a lot less words. I only have to write 4 letters that way, as opposed to the, I don't know, like 20 letters that it takes to write out data entry, mean, and standard deviation. It's just in math, we try to shorten everything down with equations. So that's an equation that I use, and let's talk about kind of why that works. We'll explore that in this next problem. A normal distribution has a mean of 50 and a standard deviation of 5. Now I've taken the liberty to go ahead and draw that out and what that might look like here. And let me clean this up for just a second. The question says, find a z-score for 55. Well, you should actually kind of be able to look at this and just tell what it is. I can see that z-score is a number of standard deviations. And it looks like that's just one whole standard deviation. Like I think my answer to this is just going to be 1. And it is. But let's use our quick formula here where we do z equals the data entry minus the mean over the standard deviation, right? The data point that we're using, this right here, is x. So that's 55 minus, and they tell us the mean of 50. The mean of 50, that's our mu, or you can just call it the mean. And then we're also told what the standard deviation is. The standard deviation is 5. So that's our sigma. So this will just be 55 minus 50 is 5. Divided by 5 is 1. Yeah, we do still get that same value of 1. So we can get it by looking at the picture and telling that it's just one whole standard deviation to the right. Or we can use our formula of the data value minus the mean divided by the size of a standard deviation. And that will get us there. Now that works really well for whenever we are right on those standard deviation values. But notice this next question is where we've got to actually start using this formula a little bit. It says find the z-score for 46. This time, 46 is our x value. That's our data value that we are looking for. So if you want to use the words, you call that data value. If you want to use the variables, we call it x. Right, so 46 is right here. And what I want to know is how many standard deviations is that below the mean? Well, I can see that if I was to go to here, that would be one whole standard deviation, so this has to be less than that. In fact, I can see that this is down 4 units and one whole standard deviation is sized 5, right? So this is like 4/5 of a standard deviation. It's down 4 units and the size of a standard deviation is 5. So it's down 4/5 of a standard deviation. Now, some of you are like, whoa, 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 you lost me. Just give me the formula. Okay, let's do the formula because, be comfortable with it. Z equals x minus mu over sigma. We'll say the data point is 46, the mean is 50, and the standard deviation is 5. 46 minus 50 is -4, so you can see we went down 4 units, and the size of a standard deviation is 5. So we get z equals 4/5, or 4/5 of a standard deviation. The last one says find the data value or the data entry with a z-score of -1.5. This means 1.5 standard deviations below the mean. Well, let's think about this for a minute. 1.5 standard deviations. That's 1.5 standard deviations. I know that a standard deviation is sized 5. So that's 1.5 fives. And I want that below the mean. I know the mean is 50. So couldn't I say start at 50 and go down 1.5 fives, right? 50 minus 1.5 fives will get me 42.5. In fact, let's go back over here and let's look and see, because we don't always have to use those formulas. You can. You absolutely can. It still works, and I will. But if we go 1.5 standard deviations, I'm going down one whole standard deviation, so that's down 5, and another half, whoops, to right there, right? Another half of 5, so to speak. So that's where you can see that ultimately we're going down 7.5 units, and that would take me to 42.5. Okay. Now, we did it just by reasoning through it. We did it by drawing it on the normal distribution. But, we can also still do this using our formula. Okay. I actually really prefer this method. Somebody showed me that, to just reason it through. And I was like, oh, that actually does make a lot of sense once you do this a couple times. 1.5 standard deviations means 1.5 fives in this sense, because a standard deviation is size 5. But let's go ahead and use our formula, and we'll say z equals x minus mu. There we go. Got that all typed in. And now we'll put in the numbers that we know. For example, they tell us z equals 1.5. So I'll put 1.5 in for z. It says find the data entry. That's the thing we don't know. That's the part we don't know, and that's our x. We do know the mean. The mean was 50, and our standard deviation was size 5. Now, the first thing that we do when we want to solve this equation is we will multiply the right side by 5 and the left side by 5. In doing that, I have 5 times 1.5 equals x minus 50, because those will reduce out to multiply by 5 and then to divide by 5. The next thing that we'll do is to add a 50 to both sides. Oh, sorry, you know what? There's one thing. This was negative 1.5, so keep that in mind. Let's add a 50 to both sides. Now what I have here is 50, and then it would be like saying plus 5 times negative 1.5 equals x. Well, 5 times negative 1.5 is negative 7.5, or 50 minus 7.5 gets me x. That's where we get our 42.5. So you can do it a lot of different ways. I hope that one of those ways makes sense to you. I would strongly encourage you to go back and practice this and rewatch just that part even. It's also a good idea to try to do this question on your own, right? Every so often in the notes, you should kind of pause what you're doing and make sure that you know what's going on. So pause the video here, see if you can figure out what z-score corresponds to 100 in this next problem, right? What IQ does Deb have? And so on. So try to do these, because I'm going to work through them now. But it's a good idea to pause the video, keep working ahead. So in some particular sitcom that everybody loves, Ray and Deb both take an IQ test, which has a mean of 100 and a standard deviation of 15. Ray is told that he received a score of 100 and that Deb scored 2 standard deviations above him. What z-score corresponds to a score of 100? Now, we could just go through and work all these and we would be fine. But this is also a good opportunity to practice making a normal distribution. So that's what I'm going to do. I'm going to draw one solid line. I'll put 100 here in the middle. And then I'll go up 1, 2, 3, and down 1, 2, 3. Next, I'm going to start going up by 1 standard deviation each time. So I see that a standard deviation is size 15. And so this will be 115, 130, and 145. And then we'll go down by 15s each time. So this will be 85, 70, and 65. Hopefully. After that, I'm just going to go up just so tall, a little more than half as tall, about a quarter as tall, and then I'll leave those other ones. From there, we're just going to connect these, though it's all concave down, changes concavity here, and it's still concave down, and it's going to change concavity here as well. There's our normal distribution. We'll go ahead and put some percentages in here. I know this feels like this might be a lot of work on the front end of this, but it makes the rest of this problem very easy. So then we have 2.35% on the in those and 0.15% on the ends. Now that we have all these values put in, answering all these questions is going to be a piece of cake because we took the time to set this up. What z-score corresponds to a score of 100? Well, hopefully you know that a z-score in the middle would be 0. There would be 0, and this is 1, 2, 3 standard deviations, -1, -2, -3 standard deviations. So the mean is 100. That means that a z-score that corresponds to the value of 100 would be 0. What IQ does Deb have? Well, she's 2 standard deviations above the mean. Like I can look down here and I can count. This is just going up 1, 2 standard deviations above. That's 130. That's Deb's score. So the answer to this is 130. Now, we can also do this by saying 2 standard deviations above the mean means start at the mean of 100 and add 2 15s, right? Because this is the size of 1 standard deviation. And we're going to add 2 of them together. So 2 times 15 is 30. That's 130. Approximately what percent of the population has an IQ between Ray and Deb? Ray is right here at 100. Deb is right here at 130. And so all we've got to do is add together our 34 plus 13.5. So that's 47.5%. About half the population, about 47.5% of the population is between Ray and Deb. What's the probability of a person having an IQ higher than Ray? Well, if Ray is right in the middle, higher than Ray would just be this way. And so about 50% of the population has an IQ higher than Ray. If you were to add together 34, 35.5, 2.35, and 0.15, those will add up to be 50%. Also, because Ray is right in the middle, right? He is average. Now, for Deb, on the other hand, Deb was here at 130. And so, what percent is higher than Deb? That would be just adding together just those two, right? So 2.35 plus 0.15, that's 2.5%. Only about 2.5% of the population has an IQ higher than Deb. Now, we've done a lot of this by hand. We've barely used a calculator for what we've done so far. The nice part about this is a lot of this stuff can be done on a calculator. And in fact, using Desmos makes this way easy. Because before Desmos and before calculators would do all this, we would have to look up Z tables. If you really get bored, go check out a Z table. Do a quick Google search. This is old school. Basically, people got together with a whole lot of calculus and did a ton of probability calculations so that the rest of us could use a normal distribution without calculus. But now we have calculators to do this stuff for us. So Desmos is great because Desmos can actually tell us the percentages of all the data that's less than or that's greater than or even between any two z-scores. From the Desmos keyboard, we are going to go to the Functions menu, and we're going to select Normal Distribution. So just like before, you're going to go to the Functions menu, and then you can see that under Distributions, the normal distribution is what we're going to be looking at today. After we get there, we're going to press the magnifying glass in order to zoom fit the graph, and then we're going to select the CDF box. So let's see what that looks like on Desmos. First, I'll hit the Functions button. I'll scroll down past the statistics. We have to keep going until we get down to probability distributions. And right there, you can see normal distribution in the upper left. So when I hit normal distribution, this comes up. Next, it said to hit the zoom fit, or that little magnifying glass. You can see it adjusts my whole screen so that I can see this normal curve nicer. And then if I tap this little arrow that's right next to the word cumulative probability, I can now adjust some numbers for what I want to do. Okay, so let's go ahead and practice with some of this. Let me put this back here for now. When we use our z-scores instead of raw values, the normal curve has we're only talking about the z-values, right? And the normal curve has a mean of 0. That's this one right here. And then each standard deviation is size 1 because we're just going up 1, 2, 3, right? Each standard deviation is size 1. The graph that we have here, where we have a mean of 0 and a standard deviation of 1, this is actually called the standard normal curve. And if we want to find the percentages of any value above or below these z-scores, we just have to adjust the minimum and maximum on Desmos. So let's find the probability that a value is to the left of z equals negative 1.53. So if we go back up and look at this other graph, we know that we could find the amount that's to the left of this, right? We know that 16% of the data, in case you forgot, about 16% of the data is to the left of 1. And also, we also know that about 2.5% of the data is to the left of 2. But it doesn't work to use proportional reasoning to say, oh, if I was at negative 1.5, I would just be halfway between those, right? That actually doesn't work for this 16% and the 2.5%. That's because you can see the area on this half is definitely not the same as the area on the lower half. So we can't use that proportional reasoning on this. And that's why we have to use the calculus, or specifically, we're going to be using a calculator. So if we want negative 1.5, what we're looking for, sorry, 1.53, we're looking for the area that's to the left of negative 1.53. And if I had to guess, it's going to be some number between 16% and 2.5%. I know that. And it's probably going to be closer to 2.5%. But you know what? We don't need to guess. All I'm going to do is go to Desmos. If I want the area that's to the left of that, the first thing I'll do is tap left on there. And then here where it says the probability, that's that P, of x is less than or equal to, and I'll put in my negative 1.53. You can see Desmos does shade it for me already, and then it says it's 0.63. If for some reason you need a more accurate decimal than that, you can just tap the little drop down arrow and you see it's 0.0630083644464. You know what? Probably just 3 decimals is good. I think we're going to be okay with that. So this is 0.063. There's about 6% of the graph is below that amount. So about 6% of my graph is shaded right now. Okay. So let's just go through and we'll do the rest of these real quick. And we have to the right of 0.93. Well, this time I'm going to tap to the right. And you'll notice that it's just using the same thing. I've got to change my value to be 0.93 now. And if you look, it says 0. That's because I actually wrote 93, right? What's the area to the right of 93? Basically 0. It's so small. Yeah. So let's go ahead and put in 0.93. There we go. That's about 17.6%, or 0.176 is fine. The next one says in between negative 1.4 and 2.7. So this time I'll select the inner if I want to be the inside a couple things, and I'll do negative 1.41 and 2.17. Pick the right numbers, negative 1.41. There we go. So this is 0.906, or about 90% of the graph is shaded right now. Once again, you can click that drop down if you want to be a little bit more precise. And then the next one, like let's say I didn't want those, I could click outer and notice that it's just the complement, right? So if I had inside those, that would be about 90%, and then outside is about 10%, right? Well, now I want to change these though, so I can use these numbers. So I tapped outer or on the outside of these, and then I put in negative 0.5, and I'll also put in 1.1. So about 44%, right? 0.444. Here you go. Make sure you practice with Desmos a lot. It's really slick and easy. You can do these on a TI calculator or on a Casio calculator if you have those graphing calculators. They work great. You'll just need to maybe visit YouTube or Google search how to do that. So hopefully this is helpful. Make sure you practice. Don't just watch me. Make sure you practice this too. All right. Good luck.